Any sufficiently advanced technology is indistinguishable from magic.
And I am joined with someone I've never met, but is probably the person I'd most like to meet of all the guests that have graced my presence, or graced me with their presence, rather, on the Into the Impossible podcast. And it's a friend of mine who's a dear human being. It's Stephen Strogatz, one of the simultaneously most humble but most accomplished people that I've ever known. He got his PhD in applied mathematics from Harvard, and he's currently the Jacob Gould Schurman Professor of Applied Mathematics at Cornell, which almost would have been my alma mater, Steve, had you guys accepted me the 2 times I applied. So, you know.
Well, it had nothing to do with me. Well, thank you. Wow, Brian, that's a very nice introduction. I feel the same way. I can't wait to meet you in person. It's going to be great.
We were supposed to meet about a year ago when I was supposed to come to Cornell to give a colloquium for the astronomy department. Many good friends over there. And something came up. There was some cancellation of most world travel. But I am hoping that the invitation will remain good and that someday I will be able to meet you in person there. And I'm actually secretly hoping to get you here, maybe by proffering an invitation during next January. When
Perfect.
I think Ithaca's not the greatest. I mean, it is a travel destination, but usually not in January.
Well, nothing compares to San Diego.
You start off this wonderful book, which we're going to talk about, although not exclusively. I'm going to try out a whole bunch of crackpot theories. I'm going to talk about the art of podcasting, because you are also a raconteur and a podcast host extraordinaire, from whom I've learned much. But I want to start off with Infinite Powers, your delightful latest book, in addition to Sync and The Joy of X, some of your most famous books. The latest book was also a New York Times bestseller, and it's just such a beautiful book. But it starts off with someone that I regret, Steve, that I never met, and it's Herman Wouk. Herman Wouk wrote The Winds of War, The Caine Mutiny, and I actually had a chance to meet him because he is the namesake of the Wouk Chair and it's woke, not W-K-O-K-E, like some people might be hearing it. We won't talk about politics today. But W-O-U-K, and he lived in Palm Springs, and he had the chair called the Herman Wouk Chair of Judaic Studies here at UC San Diego. It still exists. And I never met him, and I was always, I'll meet him, I'll take the time. It's a couple-hour drive. But he was always so vivacious and vibrant. I never thought it would be a limitation to my being able to visit. And that shows you how the truism, Steve, that no one is as dumb as an intellectual. Because I never met him, and he passed away about 3 years ago at the age of 103. But you open this book with a recollection or a statement about him and how he spoke to Richard Feynman. I wonder if you could recount that and then tell us why was that sort of the impetus for this book?
Sure. Well, yeah. So Herman Wouk was really one of the greatest, most popular American novelists of my parents' generation. So the World War II generation needed someone to tell their story. And he had been a sailor. He was in the Navy, and he wanted to write something like War and Peace for Americans. But hopefully, something that'd be popular and readable. So he was researching this big book about World War II, and he thought he should include something about the Manhattan Project, right? I mean, the building of the atomic bomb did end the war, at least in Japan. And so he wasn't sure who to talk to about this, but people told him, well, you got to go to Caltech. And while you're there, you have to talk to this guy named Feynman. So Wouk, who came from a background in, literature, history, philosophy, the humanities, goes to see this tremendous physicist, Richard Feynman. And as they talk, they start to realize they have a lot in common. They're both Jewish guys. They both grew up in New York. They both love to tell stories, have good senses of humor. And so and of course, Feynman had also served in the war. He was a very young guy working on the Manhattan Project, like in his early 20s. But they also have some big differences. That Wouk was devout, Orthodox, whereas Feynman was extremely atheistic. So anyway, they're kibitzing and they're having a good time talking about everything. And but on his way out, as Wouk is walking out the door, Feynman stops him and says, "Hey, I just have to ask you one thing. Do you know calculus? And Wouk said, well, no, he never studied it. And so Feynman said, well, you better learn it. It's the language God talks. And that then became the title of a book that Herman Wouk wrote about his conversations about science and religion with a variety of scientists over the years and philosophers and other people. So anyway, why did I tell that story at the beginning of the book? Because it does a couple of things for the book, I feel. One is it sets up this really uncanny idea that there is a language of the universe, and that language is written in mathematics, and specifically a particular dialect of mathematics, calculus, and even more specifically, the subdialect of differential equations. So I wanted to tell the story of how we as a species have come to understand the workings of anything that changes smoothly in time or space by learning this weird language of calculus that, as Feynman said, Feynman doesn't really explain what he means about the language God talks, but I think any working physicist or mathematician understands that, the laws of fluid dynamics, the laws of gravity, even quantum mechanics, all these laws are written as differential equations. And so he urged Wouk, if you're going to write about the atomic bomb, you better learn calculus. But the other thing I like about Wouk is that he stands in for the general reader, in my mind. Wouk goes on to tell that he tried to learn calculus. He took Feynman seriously, and he had a real heck of a time learning it. He could not, he tried reading books with titles like Calculus Made Easy. It didn't work. He went to a high school class. He started falling behind. He really tried. And so I felt like the reader I have in mind is someone who would like to know what calculus is about, or they're curious, or maybe they even took calculus but never saw the point of it. That's who I'm writing for, someone who is open-hearted and wants to learn, but who is really mystified by every exposure to calculus they've had so far.
Yeah, that meshes nicely with my mission on the Into the Impossible podcast. I always say it's to deconstruct the tactics of the taciturn, because the old joke, Steve, this holds doubly true for applied mathematicians, is that how do you know an applied mathematician is outgoing? Because he looks at your shoelaces when he talks to you. But actually, I've had on 9 Nobel Prize winners. I had on Jim Simons, who's a renowned mathematician and philanthropist, obviously, but also even Pulitzer Prize winners, astronauts, and very few of them are able to communicate these ideas to the lay public. And I feel like, I've kind of gotten maybe a little bit off the deep end, Steve. You should step in and intervene as you see necessary. But I keep saying it's a moral obligation. We get paid by the taxpayer, by, in my case, the state of California, as well as a public servant, to study and do things that we do for fun. The joy of what you do is evident not only in the title of your books, but in your exuberance and your irrepressibility, which is so infectious and delightful. But you would do it for free. And so,
of course, right, sure.
My point is that you studied how to be I had Neil deGrasse Tyson on last week. He was talking about how much he studies the craft of storytelling. I wonder, should we make it a requirement along with partial differential equations? Mathematicians and scientists have to learn how, if nothing else, to communicate to the people who pay their salaries.
That's a very interesting thought. We never even consider that, do we? And yet, I am actually doing that, not as a requirement, but we're offering a seminar that we call the Mathematical Communication Seminar. And I've got grad students and faculty and postdocs coming to it. It's a small group, maybe 15, 20 people. But we are trying everything to get better at this. We watch videos on YouTube of people giving Fields Medal addresses or Nobel acceptance speeches or just ordinary colloquium. Or, in other words, we try to analyze what's working or not. We read some of the best writers. We think about going on TV or radio, how do you get your message across, crafting the so-called elevator pitch in 1 or 2 minutes. Anyway, so we're trying to think about all aspects of written and spoken communication, and we don't really know what we're doing because there's no textbook for this. We're all just winging it using our instincts and using the best role models we can find to try to imitate. But yes, the short answer is yes. I don't know about requirement, but I totally agree with you that it's a moral obligation. It's also good strategy. If you want to be a successful scientist, if you can communicate well, I mean, of course, you have to have the chops. You have to be able to do the good work, have creative ideas, have the technique to solve the problems that you're trying to solve, have some luck. Even with all of that, if you can't communicate, you're not going to get the grants. You're not going to get your papers in the best journals. Your colleagues aren't going to understand or appreciate what you're doing as much as if you could really get your point across.
Right.
So,
I feel like it's a baseball, it's like Major League Baseball where, we're just teaching them how to hit home runs or run around the bases, when you hit a home run, but we're not teaching all the soft skills, all the, kind of just blocking and tackling, to mix metaphors. But now you're also we're going to get into some serious red meat, I hope, for my, or some tofu. For my don't worry, stay tuned, because I have some real-time calculus, which is always very dangerous to do, but I have some actual real-time nonlinear dynamical questions to ask the world's most foremost expert, Stephen Strogatz, who's my guest today on Into the Impossible. Before I do that, you've interviewed a lot of the most brilliant people around the world for your Joy of X podcast for Quanta. Can you talk a little bit about Quanta? I was a guest. I was honored to be on it.
Yeah, wonderful. Thank you for being part of it.
I think your standards have certainly risen since that time. But tell me, what is that like? And have you noticed this too with these brilliant intellects that, you have to do a lot of coaching and kind of get them out of their shells and really make interesting what is fascinating in these interviews that you do, and you do it so well. First of all, you had no training in that, right? It wasn't.
No, of course not. No.
Yeah.
No, well, thanks. I'm glad you feel that it's working. We would love to have more listeners.
Yeah.
So if any of your listeners would give us a try, that would be great. But it's really hard for podcasts to be discovered or to be noticed. There's a lot of people trying hard out there. And there's a lot of fantastic, things to choose from. Big investment of time for people. So we understand why it's difficult. But as far as how to get people to open up, I don't know. I mean, I like to talk to people about their lives. Often if you get someone talking about their mentors, their beloved teachers, or even their parents, it softens people up. They will get out of lecture mode, which is the default mode for all of us professors and researchers, and into just warm human connection mode. So I usually like to start with something soft like that, and then I also don't prepare very much. I don't know about you, but I have found that when I prepared a lot, that I wasn't listening as well. If I didn't know what was coming, like for instance, I had Frank Wilczek, who I think you also maybe interviewed recently. Is that right?
Yeah, I did. I was going to ask you about that specific podcast, that and Robert Digraph, when you had him on too.
Yes. Well, so Frank has done such magnificent work in physics and cosmology, or at least with implications for cosmology, some of his stuff, potentially, if he's right about dark matter and axions. But I mean, when I was talking to him, I just wanted to stroll down memory lane about his work on asymptotic freedom. What is the nature of the force that's holding quarks together inside the nucleus? And, why don't the protons in the nucleus just repel each other? I mean, they're trying with their electromagnetic repulsion, but the strong force is holding them together even more tightly. So anyway, and I have never studied nuclear physics, not really. And so I didn't know anything much about quarks and jets and asymptotic freedom. So I went in as a beginner, just knowing the words, but and Frank explained it all very clearly to me. But along the way, he talked about his father in very affectionate terms, his father who hadn't gone to, really, certainly not college. I'm not even sure if his father finished high school. So it was a really warm, nice discussion. But then by the end, at some point after Frank had finished explaining work he did as like about a 21 or 2-year-old graduate student, and he's now probably 70 or so. He's like, you want to hear anything I've been doing since then? And I did. And then he knocked my socks off by telling me in a very slow burn kind of way. I didn't see where he was going. But anyway, it ended up that something he thought of might explain dark matter in a very natural way that would grow right out of the standard model. Yeah. So, and I didn't see that coming. And you can hear if you listen to that podcast, you'll hear my audible surprise.
Wow.
At like, oh my God, what? Like you saved the best for last, I said to him, because I had no idea we were going to be talking about dark matter. So I don't know. I mean, what I'm saying is by not preparing, it gives a genuine connection if you really listen to the guest. But of course, it also makes it kind of meandery, which might be a deficit in our show. I mean, if I had more structure, it would be better. I don't know.
Yeah. Well, I find them really delightful, and what's so great is that sometimes you'll just, like the interview with Digraph, who is the director, I think, of the IAS, Institute for Advanced Study, and then all of a sudden he starts talking about art and why visual art is not as deep or effective or emotional as music. And you guys start going into this discussion of why, you can get moved to tears by music, by some notes of music, a score. He talks about classical music, but it can hold for anything. But you never start crying, the Mona Lisa. I mean, you might over.
It's interesting, isn't it?
It is. It's so.
I mean, that's an interesting point.
Going off on it, and it made me think. And I want to get your opinion, really, really on this as well. But like, if that's true, then by dimensionality, in other words, music is one-dimensional. That was kind of the thing that you guys came to the conclusion. Like, you have to get it revealed at the pace that the author wishes you to experience it, because it's a musical one-dimensional, format. Art, painted art, like this thing over here, is two-dimensional. But then maybe I was thinking, like, is three-dimensional sculpture like less moving or more moving? Like, how do you think about that? And then I started to think, what would a four-dimensional creature? What kind of art would they produce? But I found it so interesting. You don't have to react to that, but
I do have a little reaction. I don't even really remember, especially what Robert and I said. But to me, the thing about music is time.
Yeah.
The music unfolds in time, and art. Well, of course, film can unfold in time. Cinema, literally meaning something about motion, but snapshots or pictures on the wall really are at a disadvantage in terms of emotional power, because time is Robert and I did start talking about this, that the time is the emotional dimension, much more so than space. And I think because of memory, because of loss, because of dreams of the future, these are all things that have to do with time as a dimension. And also our mortality, that we get to live for a certain amount of time, but we can move through any part of space.
Yeah, I wanted to talk about that and keep on this theme, because I've had, Carlo Rovelli on the podcast, and he has a book, The Order of Time. I had on many people. I have some folks come, a brief history of time. I had on not Stephen Hawking, although I would have loved to, but I had on his closest collaborator, Leonard Mlodinow, and they talked about their writing, and Stephen, et cetera. And now I've got a lot of folks coming up, like Julian Barbour and others. But and a lot of these thoughts that people are thinking about have to do with time. And I think of it in terms of course, entropy. And this is where I'm going to tap into your expertise. So Stephen is perhaps known for, you're known for so many things. You're the father of, along with Duncan Watts, your student, the small network, small world theories, and network analysis, network science, I think it's called now, with a paper that has over 45,000 citations at last check. I think it's growing exponentially as we speak. But I started to think over all these interviews. I've done interviews with stand-up comedians, and I start to think it's interesting, because time, according to Carlo and Frank Wilczek, on, as you mentioned, Frank's basically, his thesis is that time is what we call things that clocks measure, and clocks measure things changing. And of course, that's related to the second law of thermodynamics. And if there was no change, or you were at absolute zero, you'd experience no time change. And so I asked a comedian once, I said, is it easier to make people sad or angry, or to make them laugh? Because there are actually many more ways I could make you sad right now, Steve. Right?
Please.
How can I make you happier? The state of ways I can make you. You're already very happy. You're at top university in the world. You've gotten all this acclaim. It's very hard to make you. You could win the Nobel Prize, or you could win the lottery or something. But those are very few compared to all the ways life could get worse for us.
I see where you're going. I see.
And so I'm wondering,
interesting.
When we think about these things, like, how firmly rooted is that experience? The emotion, is it intimately connected with entropy? In other words, do we experience time as so painful or melancholic because it's associated with entropy?
Geez, this is a really deep and interesting question. Yeah, whoa. Okay. I see where it's a really interesting analogy you're making, because we're taught in physics that when we think of a state that's highly ordered, it's sort of like there are very few ways it can be in macroscopically, like from the outside, there's only a few ways that you could arrange the small parts, the microscopic configurations. Geez, I'm just using a lot of jargon. It's like in short, in plain language.
Used to it.
Well, okay, but I mean, plainer language, it's like you're almost saying there's nowhere to go but down, right? If you're too successful, or if things have worked out well for you in your life, or you've had a lot of luck, you get a natural feeling of concern, like my luck is going to run out. And that's because you're in this highly negative entropy type state, right? I mean, you're in a very abnormally ordered or lucky state. And so eventually the laws of chance will catch up with you and your luck will run out. And you're going to get sad as a result. So it's a really interesting analogy. But you're saying somehow the wistfulness or the melancholy of time is a direct, like, emotional response to the second law, that things tend toward greater entropy. And I don't know. I mean, certainly aging is a kind of entropy, or, or is, I'm just sputtering. You caught me not really knowing what to say. You want to help me out? Do you have some thoughts? You want to give me some of your thinking on it?
I've got a couple of follow-ups. Actually, yeah, because of this notion of small world networks that you and Duncan, your student, worked on a couple decades ago, it got me thinking a lot about networks and for good and bad. And where I'm eventually going to go with this is the relationship between entropy and networks. And I'm just not clear if such a notion exists. But here's what I was thinking along the lines of what I just said. I have a big family, a bunch of kids, happily married, and but there's sort of, I was making this argument, to a friend of mine who's single. He's a perpetual bachelor. He's scared to commit. He doesn't want to have kids. He's having fun with his girlfriend. I said, you should not only get married, but you should have as many kids as possible while you can.
Yeah.
But there's some biological limits on it, if you don't know. But also, I made the argument from network theory. So if you have a family of size n people, then there are exactly n choose 2 pairs of relationships, of dynamics.
Yeah.
And there are all these like sayings, and I was trying to figure out, can we construct the thermodynamics of happiness, the entropy reduction that occurs when families have a lot of kids? And I've noticed that happy family, like big families, they can be unhappy, of course, but I come from my adopted family was a family of 10 brothers and sisters, and they were the happiest people that I knew, the Keating side. And I started thinking, how many pairs of relate? And so I went through it, and you can do the math very easily. And it comes out, for that many networks, it grows basically quadratically, right, with the number of. But the cost of having n kids, probably grows linearly at the number of kids, right?
Probably. Yeah. Although in terms of interactions between the kids, that can cause it to be difficult to deal with them. Right. Because sometimes they have their own. So there might be a little bit of quadratic or even cubic terms in there. But yes, okay, let's first stipulate that, probably the cost is proportional to the number of kids, roughly.
So you only need one minivan, you only need one house, you only need, whatever.
That's true. And some of them are independent of the number of kids. Like the minivan, it doesn't matter if there's 4 or 5 kids, exactly. Right? They all,
So sort of the benefit, because there's a saying, Steve, I'm sure you've heard it, you're only as happy as your least happy kid. And
yes.
You have 2 daughters, and you always talk so nicely about them. But if one of my kids is unhappy, it's true. But is the converse true? Are you, can you be as happy as your most happy kid? Maybe. And if so, would the happiness function grow? What I'm getting at is you should have more kids because the benefit grows as n squared, but the cost grows as n, so the net benefit leads as n. What do you think about this crackpot theory?
When you say, so the n squared benefit is because there's all these relationships. So you're sort of implying that individual kids, because they have more possible partners to goof around with or have fun with or have heart-to-heart talk with or whatever they need to do.
Yes. And by the way, they're going to spend half their lives without us, right? I mean, the average parent, dies at a certain age, and then the kids are left with themselves. Their parents aren't around half their lives.
Well, it's an interesting argument. It doesn't occur to me because there are also other costs that you put on society by having too many kids. Sure. Though you could decide you don't care about that, and it's every family for themselves. I don't know. We made the decision to have 2 kids and stop. because we thought it was nice for them to have each other, which it has turned out to be. Being in an ecosystem, a family with two people your own age approximately to grow with and to fight with and to just, all the things that make life interesting seemed to us more desirable than just having one child or zero. I kind of grew up effectively by myself. I did have a brother, and I do have a sister who's still alive. My brother passed away, but they were much older than me. My mother had been married before, and then her first husband died, and she had these two little kids. And then my father married her, and then they tried for a long time and eventually had me. So my brother and sister were 12 and 10 years older than me. So effectively, I was like psychologically an only child. In the house, nobody picking on me, nobody doing irrational stuff. It was and speaking of entropy, everything was clean and well-ordered and well-regulated. So what it meant was, like in relationships later in life, people would yell at me or get mad at me or have fights with me. I was always pretty terrified of that because I never had anybody picking on me or being crazy. So, I think it sort of set me back in a way. Like having brothers and sisters around, I think is very developmentally healthy for people to learn how to deal with conflict and other stuff. I didn't really have that.
Yeah. No, it's sort of the same argument I hear, where people shouldn't homeschool their kids, because then they're only getting exposed to, this very small network, and they're not getting diversity of opinion or backgrounds or what have you. But that was just something interesting I wanted to run by you. If you thought it was totally crazy, I'd stop thinking about it. But I want to turn now back.
There's also a linear cost to the person bearing the children.
Yes, of
course. Maybe more than linear, because what is it like to have 4 kids versus 5 physically?
Right.
I don't know. So this might be a very male-centric thing we're expressing here. How does your wife feel about the idea of a large family?
Well, I keep saying, we're at least halfway done, once we hit the magic numbers that we, so maybe turning away from families now back to calculus.
Okay.
Wonderful book. Although before we leave that, Steve, is there a notion of does entropy come into play at all in network theory or network science? Is there with clustering, is it beyond just a counting of states? Is there some way to classify a network?
It's a good question, and I haven't seen people talking about entropy. There are ideas of curvature. You can have discrete versions of curvature, just like we have continuous curvature. But does entropy generalize to network? We have entropy in dynamical systems we certainly talk about. Aside from thermodynamics and classical physics, even in nonlinear dynamical systems, there are people that calculate things about information and entropy and all of that. So those ideas do work outside of statistical physics. But I haven't seen anyone use them in networks that I can remember, but it seems so natural. It's such a powerful idea. Yeah. So there must be. I'm just not up enough on the literature to give you a good answer on that.
It might be. Getting back to calculus, so again, your part of your mission was to evoke Herman Wouk, who was a very educated. I think of him as a Renaissance man in our century. He was someone who was incredibly curious. He actually ended up writing a book, as you know, called The Language God Talks. He wrote a book about the superconducting super collider cancellation. He's a very brilliant and peripatetic intellect. But I forwarded, your. I gave a copy of your book. I bought many copies. One I gave to one of my guests, whose name is Kamal Ravikant. He wants to learn quantum mechanics, and so I said, well, the only way to learn quantum mechanics is to learn calculus, and the only way to learn calculus from now on is going to be me giving out copies of your book, Infinite Powers. So I want to thank you for that. Your book is based on, and I gave it to my father-in-law, who knew Herman personally. And he said that the eventual book that he wrote combined Herman's curiosity about physics and mathematics with his traditional Jewish beliefs about faith and God. Maybe later, if we have time, I'll talk about the proliferation of books and things about God, the God particle, the God equation, the mind of God, all these God references by atheist scientists mostly. But anyway, I gave my father-in-law your book, and he said, I was surprised by the reference to Herman Wouk. And as I have gotten farther into the book, I am overwhelmed by the author, Stephen Strogatz's skill as a writer and a storyteller. the description of Archimedes' work and humility is so amazing. Now my head is full of triangles. Also, and this is, he's not a young man, and he's very brilliant, but he's not inclined to mathematics whatsoever. He goes, also, there is a spiritual quality about Stephen's book that brings together mathematical discovery, music, art, and the idea of infinity. I wish that all mathematics could be taught this way. Many of us who hit the wall with calculus, those half steps, would have made it through if we had Stephen. So I want to commend you on that, and I want to highlight this infinity principle. First up, I'm going to ask you a rapid-fire question. Can any entity, any mind known to exist, comprehend the concept of infinity? Even a computer. Can a computer comprehend infinity?
Well, I'm sort of stuck on the word comprehend there. I mean, we can certainly define it in various ways mathematically and work with it. I guess I'm thinking in terms of like visceral understanding versus intellectual understanding. I can operate in a consistent way with various types of infinity. So to that extent, I think a pretty ordinary mind can comprehend it in an operational way. But can you really absorb it in your bones? Well, I don't know. It's through the ages. This has been something that has inspired all kinds of feelings in people: dread, the fear of bottomless pits and the abyss. And I mean, some people say that you can go crazy thinking about infinity, like that you really shouldn't go there. So I don't know. I mean, it's tempting to say, no human finite mind can really comprehend infinity, but I don't really know what that means. Mathematically, it feels like we know how to operate with it.
Mm-hmm. My claim is that, I'm not really that worried about, alpha zero, you talk alpha infinity, whatever. I'm not worried if computers can beat human beings at chess. That actually doesn't concern me, or I don't think about that as an important question, because I know it's true. But I wonder, can a computer create chess? Can a computer create the game of Go? In other words, can it come up with the idea of infinity? I don't think it can. I think it's something unique about human beings, and that's why, to me, Stephen, calculus is a uniquely human, as the old, someone once said, some mathematician, you'll correct me, that, God made the integers and all the rest is Menschenwerk. But I think, but only humans could come up with calculus. Just like I think only humans could come up with general relativity. Only humans can come up with things that are derivatives of calculus. No computer can. Do you agree? Or
doesn't sound right to me. Yeah, I doubt that's true. Mm-hmm. Just on principle, because I don't believe there's anything fundamentally mysterious about us. When I say here, the word fundamentally is doing a lot of the work. So, in other words, I'm a completely materialist person when it comes to this sort of thing. To me, we're not that different from the machines. We're made of atoms that came from stars. We're organized much more brilliantly and in a sophisticated way than any computer for now. So of course we pat ourselves on the back that we're much, no computer could ever do what we do. But we've been saying this for a long time, and we keep moving the goalposts. It used to be no computer would ever beat us at chess. Now that they've done that, we regard that as a trivial activity. So now we say no computer can recognize a woman pushing a baby carriage across the street. They're still terrible at pattern recognition, but they're going to solve that too pretty soon. And I mean, I'm, I guess, like an optimist. Of course, it could be real trouble, but I sort of think that computers in principle should be able to do everything we do because we're made of the same stuff. And I don't think there's anything extra in us. They're faster. They have better memories. They're just not there yet. So, but if I'm wrong about that, which of course is quite possible, if there's something like soul or, a fundamental thing that makes us human, like some spirit of God in us, like if you were a Christian, and I don't know if the Holy Spirit would come into play here, but something that's ineffable beyond physics, then sure, then computers will not be able to do it because presumably they don't have what we have. But I don't believe any of that. I think we're made of star stuff like everything else.
It's interesting. I wasn't thinking to go there, at least not this soon in the podcast, because talk about God and all these. I love that you do and that you did. I was thinking more practically, because you say something so brilliant in this book. You say when you see like an infinite, like when you see pi, I used to think of it as geometry, but you say no, it's calculus.
No, it is. Yeah.
And I used to think natural logarithm. You say, no, think calculus. And I think just from a practical standpoint, 1/3, you can't represent that unless you had an infinite computer, right? So the
well, it depends. I mean, 1/3 is perfect. 1/3 is perfectly fine if you work with fractions.
Right.
But if you want to start converting into decimals, that's the thing. I mean, because of being 10-fingered creatures, we like to massage our representations of numbers into this decimal format. Yeah, 1/3 doesn't play that well with decimals because it forces you to take infinitely many threes after the decimal point. But, you get used to that. And also, in the spirit of physics, if you just want a good approximation to 1/3, you take as many threes after the decimal point as you need and say good enough. And actually, it doesn't take that many to get an approximation better than, the scale of the Planck length or whatever we think the smallest amount of space or time will be in physics. So for all practical purposes, you could compute very well with, I make that little calculation in the book that if you measure the length of the biggest thing we know, say the diameter of the known universe, something you've thought about, I know, and you taught me about, actually. I was surprised, actually, when you told me it's more than 2 times the, it's not just the age of the universe times the speed of light times 2.
Right.
Because what? Because inflation was going so fast at the beginning?
Or even if there wasn't inflation, just the expansion of space itself is taking place independently of time or can take place faster than the speed of light.
I guess because no signals are getting sent. There's no speed limit or...
That's right.
Okay, but anyway, we're off in a different place there. But... But anyway, the basic point was, I think, still correct, that if you measure this whole size of the universe, its diameter, in terms of the smallest distance we know, the Planck scale of quantum gravity, you need something like 60 digits. So in other words, talking about pi that's now computed to 50 trillion digits, is big overkill if you just want practical things. But on the other hand, if you just want to think about, that's why real numbers are so unreal. Right? There's nothing in reality that corresponds to real numbers, but yet they're mathematically very beautiful. You can't really do calculus without them.
Right. So you would think that, I'm surprised in some ways that you would think that a computer, I think of things, maybe it's because of your, just profound expertise in applied mathematics, but in the pure mathematical sense, and again, just because you're not a pure mathematician doesn't mean that you don't know infinitely more than I do about pure mathematics. And I guess I'm thinking of things again with regard to entropy. In other words, there are many, many more unprovable things than are provable things. And especially given Gödel in the language of, it seems to me that Gödel's theorem combined with Turing's proof of what is and what is not computable would suggest that there's really a tiny number of things that are computable in by computational standards, and then layered on top of that as an even greater filter, the paucity of things that are mathematically self-consistent via Gödel would mean that there's almost like a very small number of things that are mathematically true and computable. So therefore, how could a computer come up with calculus like ab initio? How could an artificial Galileo come up with Galilean relativity? Or how could an artificial Einstein come up with the general theory of relativity? It seems like there is something different. It can't be purely computational, thanks to Turing. It can't be purely mathematical, maybe thanks to Gödel. So how can you say, sorry to sound like I'm on 60 Minutes, but
no, it's good
that you think that a computer could, comprehend infinity, or could, whatever comprehend means, or actually invent the concept of infinity, like just given.
For me, these questions are always easy because I can retreat to saying that, well, a computer has done it. We've done it in this belief that we're nothing special. With regard to this question, that we're made of particular kind of, wetware, the biologists would say. We happen to use carbon and water and all that in our cells instead of silicon. And we have our neurons running at, kilohertz or something instead of gigahertz.
Speak for yourself. Speak for yourself. Mine run at millihertz here.
Anyway, I just don't see any real particular obstacle that human computers have done these things over the course. Now, okay, if I were to push back against my own argument, I think the big deficit that computers have is they don't have bodies yet, right? They don't get to move around in the world and sense the world the way. That's our big advantage. We have bodies with interfaces. We have eardrums that vibrate when sound waves hit them. We have fingertips that, we have all kinds of things. We have obviously, eyes, everything else. There is computer vision now. I suppose computers can hear. I mean, my microphone right now is hearing me. So once computers get better at sensing the world and get to move around and have, the other thing is emotions, right? That's interesting too. Computers at the moment have not, as far as we know, been imbued with emotions. And we have desires, including the desire to understand, to think, to create. They don't have any of that. So they're really missing a lot of important stuff. And so, yes, they haven't thought of calculus yet. They have proven theorems in very creative and even elegant ways. They've been told to do it. They haven't been taught how to do it. I mean, they've actually invented. See, this is why I get emotional about computers, because I am a very active and interested chess player. And when you see the games of the best chess programs now, they don't play like machines anymore, even though they are machines. They play in this very romantic, swashbuckling style, sacrificing material. They look like they're imaginative. Now, you could say that's just stupid. Of course, they're not imaginative. They're just machines. But then what are we? I don't know. I mean, we think we're imaginative too, but we're just using parallel processing anyway, I'm kind of sputtering, but I kind of don't see the argument for anything particularly special about us. You can also go in the other direction. When I think about my dog, when I see the emotions on my dog's face, I know I'm not kidding myself. Some people who don't have animals will say, yeah, you're being soft. It's not true. Your dog doesn't feel anything. Your dog doesn't really love you. Your dog doesn't miss you when you're away. But anyone who has a dog knows that's wrong. That's not true. Of course they do.
Right.
So,
and the dog makes it into the acknowledgments of infinite.
Yes, Murray is in the acknowledgments. Murray was a very good companion for me when I was walking a lot and thinking about the book and frequently dictating into my iPhone. I wonder how you wrote your book, actually. I mean, when you wrote Losing the Nobel Prize, did you type? Did you talk to yourself and record it? What did you do?
A little of each. I did some of each. Sometimes in the shower, it's a little inconvenient to have a notepad in there, so I would record on my iPhone, or I had a bunch of notes, and so that's how I did it. But I didn't have a dog. I only had 3 kids running around at the time. But actually, that leads me into something I've always wondered about mathematicians. When Feynman used to wonder about this as well, and I wonder how you think about it. When you count, let's say you're counting to 10. Do you see numbers moving through the air? Or in your mind, or do you count 1, 2, 3? Because I know for me, I have to sing the alphabet song to get what letter comes after X. How do you visualize number? How do you count? Just practically speaking. Ask a mathematician about numbers. They'll be like, what's that? Yeah,
counting. Why would I count? I think I would do what you described. For me, it would be sonic. I would hear it. And same thing with the alphabet. I can't, if you said, where is L in the alphabet, or what comes after L, I would hear it in my head, LMNOP, like that. So yeah, it goes way back to childhood, and it's very auditory for me. I don't picture the alphabet on the molding of my, first grade classroom, so I don't see it. Mm-hmm. But the math I do is very visual. So I like chess, and I like thinking about the pieces moving around on their 2-dimensional checkerboard. My subject is dynamical systems, which is all about things moving around either in real space, like planets in the solar system, or imaginary things moving around in an imaginary space that we call state space, where each point represents the state of a hard cell or of a population or whatever, a bunch of concentrations in a chemical reaction. Basically, the idea is to describe a state of something, you have to give a lot of numbers, saying what's the concentration of this and what's the voltage across that membrane and whatever. You give all these numbers, and each axis represents one of those numbers, and you could have 100 of them, and then you think of that as one point that's an ordered 100 tuple. 100 numbers separated by commas, and we picture that as a point in a 100-dimensional space that moves around as the state changes as time goes on. Except we're not really picturing it. I'm taking liberties there. What I'm really picturing is 3 dimensions, and something's flying around in 3D, like a drone flying around in space. I have my imaginary point moving around in 3D, but I pretend it's kind of 100-dimensional.
Interesting. So, also thinking back, if we can go back to networks and friendship and stuff like that. One of your previous book on calculus was called The Calculus of Friendship, which I haven't read, but I was wondering if we could explore a concept that made me think of at least the title of the book, but maybe some of the work that you've done as well in networks and so forth. But that was this week's Torah portion, and we should say we have talked about the Torah in the past, but this week's Torah portion revolves around gossip. Oh. And the gossip that is engaged upon can be manifest in a human being back in these days, at that time, 3,000 years ago maybe, that you would actually have a physical symptom, like your hand would turn white. It was called leprosy, but they don't really think it was leprosy. They don't know what it was. But it made me think, and actually gossip is considered the most one of the most awful sins, because it's basically a sin that's impossible to repent for. There's a famous story of a man who told tales about his rabbi, and they were truth. I mean, the whole point about gossip is that it's true. If it's false, it's a lie, and so it's sort of less pernicious. But anyway, this man is telling a story about his rabbi. It gets back to the rabbi. Then the guy goes to apologize to the rabbi. And the rabbi says, and he says to the rabbi, "How can I make amends to you? I feel so sorry for the harm that I've caused your reputation." And the rabbi says, "It's very simple. Just go to your house and get a pillow." The guy's like, "Whew! I thought it was going to be a hard form of teshuvah, of repentance." And the rabbi says, when he brings over the pillow, the man goes, "Okay, here's a pillow. I didn't know you needed a pillow, but here you go." And the rabbi goes, No. Just simply, I want you to cut it open and go in the town square and just shake it out. And the man goes, "Okay, fine, if this will absolve me of my sins." So he does it. And then the rabbi goes, waits a couple of minutes and says, "Now go pick up all the feathers." And the implication being that it's impossible to do that. It's impossible to redo that. But I wonder, is that one of the perils of networks and small or big, is that, there is harm that these things can land at any place, and they're almost irreparable. And you see that obviously with social media and things that grow, virally. There are perils of these networks as well. And I wonder, are we a victim of these networks? Are they kind of just so ingrained? You make the point, brain cells or neural networks act this way, human social networks act this way. Are they like the microbes? There's like more microbes than human cells in the human body. Mm-hmm. Are we like at their mercy of networks, or are networks something we can master and subdue, as God says?
Oh, I worry about it a lot. I've been worrying about it a lot. I wrote a little essay some years ago. People could probably find it on the internet easily. It's called Too Much Coupling. Uh-huh. So there was an EDGE, John Brockman's group, yes. EDGE. He asked scientists, maybe you've written for them too.
Yeah,
they often
Katinka, who was your agent, I guess, or she was my friend, and John Brockman. Yeah. Mm-hmm.
They often ask they've stopped doing it, but they used to ask at the end of every year, what's some question, and then people would answer the question, and they would now frequently be collected into a book. So one year, I think the question was, what are you worried about?
Yes.
And I worried about too much coupling. Now, what I mean by that is coupling is a word that we use in dynamical systems to describe the influence of one thing on another. I mean, I guess it comes from the old days when you would have two train cars coupled together by, iron that grips one to the other so that they're attached. We speak of a couple, like people who are a couple, they're connected. So coupling is when two things are connected in such a strong way that they can really affect each other profoundly. And when you have, instead of just individuals, you have a population of individuals that are interacting like people in a social network, or like species in an ecosystem, or all the different cells in your heart, or whatever. These are all coupled dynamical systems. Now, we learn in dynamics that often as you increase the strength of coupling, if you let the individuals hear each other a little bit more or influence each other a little bit more, there's often a phase transition when something qualitatively dramatically different happens that you couldn't see coming. I mean, an example is on the Millennium Bridge in London, when people were walking across the bridge on opening day. It's a footbridge. If you've been to London, you may have walked across it. It's a beautiful thin footbridge.
Yeah.
But on opening day, the crowd was so big that they ended up setting the bridge wobbling side to side in a way that was very uncomfortable for people, and they had to hold on to the railings. But what was weird is that as the bridge started to wobble, people got in step with the wobble because that's a common human reaction when you're walking on a wobbly surface that's going sideways. Like if you stand up on a train that's moving fast and it starts jiggling, you may spread your feet out wide and walk in step with the vibrations of the wobbling train. People walked in step with the wobbling bridge and inadvertently pumped more energy into the bridge, which made it wobble more, until eventually you had whole vast crowds walking in step, not on purpose, driving the bridge. Anyway, they had to close the bridge, and then repair it, and now it doesn't do that. But the point was that the bridge engineers couldn't see this transition to spontaneous synchrony. When they did tests of the bridge in their computers simulations, it didn't do this. And it's only because later experiments showed it's only when there were enough people on the bridge it suddenly started to do this. Below that, nothing. So when I worried about too much coupling in this essay, what I was talking about is that we're doing a lot of social experiments on ourselves at global scale, and we don't know what the heck is going to happen in terms of phase transitions. The internet has done this to us. Now the pandemic is doing it to us through airline networks. Viruses are traveling across the world. Nazis can find each other much more easily than they used to, thanks to the internet. All kinds of things, and things that we can't even anticipate now. I'm sure attacks on the power grid or other things are all being made possible because of this enhanced connectivity that we are walking right into. So I don't know what's going to happen, but I worry about it a lot.
Yeah, I found that essay as you're chatting, and I was listening as I work with my millihertz processor, and you made this really kind of ridiculous claim, Steve. I have to call you out on it as one of the problems of such coupling. This ludicrous idea that it could lead to a worldwide pandemic, and I just want to give you the chance to recant that.
Well, right. So this essay came out when 2013 or something like that. Yeah. No, it was obvious. Of course, I wasn't alone in imagining that this could happen, and it will happen again. These things are just in the nature of the modern world now, and we haven't even yet endured the worst of it. On the other hand, there's been great benefits for this interconnectivity. Think of all the great stuff you can watch on the internet now, or even this podcast that we're able to do, and you can reach people. So education, I think, has improved in certain ways because of it. I love being able to find great performances by some of my old musical heroes. That's all there on YouTube now. So I appreciate some of the...
I got a text or a Twitter message from the national champion of chess of Nigeria. He wanted to be connected to, he wanted to play like a speed chess game with me. And I said, well, my rating is probably the logarithm of yours. But I referred him to a Cornell graduate by the name of James Altucher, who is a well-known podcaster as well. And so hopefully they'll play a game, and maybe the world will be richer for it. But actually, it comes to pandemics. I was noting to one of my friends at one point, like during the pandemic, that flatten the curve was really a calculus notion, and really that more people learned at least one thing about integral calculus from the pandemic, at least. But yes, in this notion of kind of the unbounded power for good or bad of networks, I think we have to be quite careful. I want to ask you about math as a mathematician, and this notion that we have. As I mentioned before, I'm having people like Michio Kaku on. I've had on the colleague of Stephen Hawking, who ends his great book, A Brief History of Time, with an exhortation that if we find the final theory of everything, we will know the mind of God. And Michio Kaku's new book is called The God Equation. What do you make of the fact that, and of Feynman's, the language God talks? What is this about, this notion of God? Is it just a stand-in or kind of a call out for authority's sake? Why do physicists, who are mainly, fellow members of the National Academy or American Academy of yours, those people are mostly secular, right? So what is this notion of God? Why does it come up so often? What do you make of it as a materialist yourself, as you say?
Well, I'm not sure why different people do it. I found myself doing it in my writing, and my wife pointed it out to me. She said, "There's a lot of God in this book."
Yes.
As she was reading some of the chapters, and I was not really very intentional about it, but a lot of the great scientists have been religious. Certainly Kepler was. I mean, Kepler studied to be a minister before he became Kepler, the astronomer and mathematician. And Galileo, who often is championed by atheists because of his standing up to the church, or at least trying to for a while before he had to recant, understandably, otherwise get killed like Giordano Bruno did. Galileo was, as far as I can tell, not an atheist. Galileo seemed to want to reveal God's handiwork. He thought he was doing something very devout in figuring out what God had created in the laws of motion, and so I don't think he found it particularly. I mean, it's true that the church was taking some heat from Galileo, but the church is different from God. I mean, in his mind.
Yeah.
So, and similarly, Isaac Newton clearly was very interested in God and spent a lot of time writing biblical chronology, trying to figure out when the world was created. And anyway, so
you know what he claimed was his biggest accomplishment, Steve?
Absolutely, his work on the Bible.
Well, right.
Go ahead. You tell me specifically.
He died as Christ did, a virgin. He claimed that was
I haven't heard this story.
Yeah, but I've also found a lot of, what is thought about Newton, in particular. Have you heard this story, Steve, that the law of gravity had to be modified, basically introduced this god of the gaps, kind of injected himself into the laws of gravity to stabilize the solar system against the gravitational instability of resonance phenomena. So when the planets every so often would come together, their orbital periods would resonate, and it would cause a dynamic instability. And apocryphally, Newton injects God, but actually a guest also by the name Stephen Meyer, who's an intelligent designer, I should say, he pointed out that you can find, and he was a philosophy PhD from Cambridge. He's a very well-respected philosopher. Anyway, he points out that nowhere does Newton ever make that claim.
I don't believe. I've never heard that either.
Yeah, but I have heard that from actually Mitchell Kaku mentions that in the God equation. Neil deGrasse Tyson mentioned it. I
find both of them pretty unreliable historians. I would not listen to Neil or Mitchell on a lot of things. Honestly, I think I'd like to have some discussions with both of them.
Yeah, me too. Although I have, and maybe I
tried to be very careful with the history. I really did. I tried to read the best historians I could find. You see, it's interesting. There's a lot of mythology about our heroes, the scientists, and we tell stories. You'll notice I don't tell the story of Archimedes and the bathtub. I don't tell the story of Archimedes getting stabbed by the Roman soldier and saying, after he says, "Don't disturb my circles." So much apocrypha in the stories that we tell of scientists. So you really do want to learn from the historians who have looked carefully at this. And so I did try to do that. But back to your question, why so much God talk from people who don't believe in God? Yeah. When we're thinking about these awesome topics about the harmony of the universe, it's natural to start to become a deist or something. This feeling that there is profound mystery in the structure of the laws of the universe. The big question, for me, would be, where do the laws come from? There's so much math in the universe. I say calculus is the language of the universe. Well, how can that be? Why? Why would it be like that? And I don't know. That's a big one. I often resort to some kind of multiverse style argument that the universes that don't have properties that are mathematical enough probably are stillborn. They can't support structure that's sophisticated enough to allow life to exist to ask the question. So we just happen to be, by luck, whatever that means, in a universe where it's all mathematical. That's not very satisfying, and I don't know if I really believe that. I can see why people want to say, because God made it like this. But then I can't really make peace with that explanation either. So I don't know. It's all very mysterious. We talked about this before, right? The Torah says maybe you shouldn't ask about the beginning.
Yeah, well, the Torah is kind of silent on it, but the rabbis in the Talmud, the second holiest.
I should say. I mean, in Bereshit is what I was talking about with the interpretation, the midrash.
Right. They said be careful, which is a good thing that we don't follow it at the NSF, under grant proposal renewal. The Talmud for the grant proposal. But it is true. There are so many myths that you bust so beautifully in this book, including like the hatred of Leibniz and the smallness of Newton. Although he was a character, I think.
Newton's a character, but I didn't really spend any time about so many calculus books would spend a lot of time on the rivalry or the priority dispute, mainly between Newton and Leibniz's followers. Leibniz had a whole army of people making the case for him. Leibniz himself seems to have been very impressed with Newton, as he should have been. I mean, he tried his best to keep up with Newton and would send him his best work. But it became clear to me as I read their original papers that Newton was really in a different league. He really was. And that's why we talk about Newton and we don't really talk about Leibniz. They're an order of magnitude apart in mathematical depth. Leibniz was great, but Newton is really unrivaled. Maybe, to me, Archimedes is in the same league as Newton. Einstein, not too many. A lot of people like Gauss as a mathematician. I'm not very partial to Gauss. I don't like Gauss very much. I like Euler, though. I would put Euler in the league with these other people. But there are only a few.
Interesting. Oh, wow.
Oh, have you not heard this about Gauss? Mathematicians deified Gauss. I don't like Gauss. Yeah, I don't like Gauss too much because there are stories about Gauss. Now, these might not be true, but the stories are that frequently Gauss would discover things and then keep them in his drawer. And so over and over again, young mathematicians would come up with great things. Oh, look, I've discovered non-Euclidean geometry. Well, no, you haven't because I had it 20 years ago. So Cauchy's theorem, well, Cauchy didn't really discover it. Gauss already knew it. So Gauss did this to a number of people, and I don't like that. I don't appreciate that. Anyway.
Yeah, he was kind of a pill, it sounds like.
Just publish it. You figured it out. Why don't you publish it? And then especially to do that snaky thing, hiding it, and then ruining it for the next person to discover it. And meanwhile, the world could have been farther advanced but he had this expression, few but ripe. That's what he would say. The results were few. He would wait till they were ripe. Few but ripe. Wow. I don't like it.
No, that would be great. That would be another good book. And my fantasy when reading this book was like, what if we did a science fiction, fan fiction book about Newton if he never was into alchemy or, spent less time, torturing counterfeiters. Although you might not, do you know this, why coins have ridges? Do you know why, like a quarter has a ridge?
No, I don't know. Why do they have ridges?
Have you ever looked at a quarter? So you should look at a quarter sometime because they have ridges, but pennies don't. And so why does one, or a nickel doesn't have a ridge, but a dime does. And so you go through it. And those are called flutes, or there's another technical name for them. So back in Roman times, what people realized, and actually this goes back even further than that, but Roman times, what people would do is they take a quarter or whatever it was back then, a ducat or whatever they called it, florin, and they would grind it down. And they would grind down the gold or the silver coin, and they would get off just enough material that they could eventually get enough coins together. They could have a whole new coin. So it's called, there's a form of inflation, and it was a form of counterfeiting and coin clipping. So for thousands of years, this was a big problem. In fact, it was a problem in medieval England in the early part of the second millennium. So much so that our fellow Jews were accused of being the ones responsible for it, and it led to the Jewish expulsion in the 1200s of all Jews from England. And actually, the problem was solved by Isaac Newton. He realized he could take a coin and put ridges on it, and then it could not be ground down without making it evidentiary to anyone who looked at it. So actually, and then soon thereafter, the Jews were permitted to move back to the land of England. So it's very interesting that he did so many interesting things. But I still would have liked to know what would his life been like if he didn't practice alchemy and also you imagine how many things he could have done. He could have had a real career, Steve.
He could have been somebody. He could have been a contender.
Now, here's another thing that I can't help but. By the way, I read this book twice, but the first time I read it, it was slow and leisurely. The second time I read it just recently, I read it in like a day. It's such and it's 300 pages. It's not like some lightweight book, Steve. And it's not, you know, it's a book with a couple equations, but not too many. Some series, some equation. But, you know, as I'm reading it, I'm thinking, well, what if Steve's wrong? You know, he's been wrong before about this pandemic thing. No.
That's for sure.
What if there's something to that stands in relation to calculus, as calculus does to, you know, algebra or linear, whatever? In other words, are we sure we have the final theory of math?
Oh, yeah, I don't make any claim about that.
No, I know you don't. But what if there's even like more than infinity? You call it the infinity principle. Is there something? Is there a possibility? There's your co-author. No. There's your muse.
Sorry,
you and your muse. Could there be math that we just can't discover, or would universes that produce higher order math be stillborn in the multiverse of mathematics?
Oh, I expect there's a lot more math to be discovered, and probably a lot of it will be beyond us. I do imagine a future where the greatest mathematicians are the machines, and they're discovering fantastic things. And hopefully they'll become good teachers. That's what I'm really hoping, you know, that they will find ways, or maybe we can program to have ways of explaining things comprehensibly to us so we can share in the pleasure of their discoveries. But I don't picture us being the greatest mathematicians for much longer. I think we're already seeing it. I mean, there are a lot of examples now of computer-assisted proofs. There are also theorems being proven by computers for the first time. So, for instance, there's a lot of results now, like the famous four-color map theorem. You know, that you could color any map with just 4 colors so that no two neighboring countries have the same color under certain constraints on what's allowed as a map. That the best proof of that, it took a long time to prove it. We finally got a proof, I think, in the 70s. Hawken and Appel, I think, get the credit for that first proof of the 4-color theorem. But they found, I mean, other people showed that there was a way to reduce the infinitely many possible maps to just a finite but large number of possible types of maps. Like there's certain equivalence classes of maps. And if you could check that the 4-color theorem was true for each of those types, you would have proved the theorem for all infinitely many possible maps. And no human being was able to check all those types, but computers did. And so we now know that the 4-color theorem is true as of the 1970s, but it's a big disappointment to mathematicians because we kind of already believed it was true. We wanted to understand why it was true. Why does it have to be true? And the computers have not explained that to us yet. And maybe they don't know why themselves. They're just calculating and don't have any insight. So that's where I think the interesting future is for math and possibly for science, is this question of insight. Like right now, and ever since Newton, we have cherished insight that not only do our laws of physics and to some extent chemistry and biology tell us what will happen, but we can see why it will happen. Like, you know, you can explain Kepler's laws with Newton's laws. So we, in that sense, understand why Kepler's 3 laws are true, that they follow mathematically from a deeper law, from Newton's laws of motion and gravity. Or similarly, why Newton's laws, you know, follow from Einstein's and stuff like that. So that's very satisfying when we have that kind of insight. But I picture that the window is closing on that we won't have this kind of insight for much longer, but the computers might. And then we'll really feel left out. That they, you know, anyway, I'm totally wild speculation, maybe all wrong. My friends in artificial intelligence, like actually Melanie Mitchell, who's one of my guests on Joy of X, coming up in a few episodes, she thinks I'm completely wrong and that I ought to take some computer science and learn more before I go mouthing off about AI. And I'm sure she's right. She says this is totally wrong. Computers are not nearly as good as you think they are. But I don't know. Okay. Anyway, this is what I currently think.
Well, it's interesting that you say that. Maybe the last thing we'll say before we turn to the wind up the episode. In the book, you say something which I agree with, you know, as a physicist, but I found it surprising coming from a mathematician. You said something like intuition comes first and rigor comes later, as it did with Archimedes. So in other words, you go through this wonderful example of calculating the area of a parabolic segment. But, you know, it's sort of led by intuition. Of course, we couldn't prove it until thousands of years later. But I always thought that mathematicians don't rely on intuition, really, that, you know, and that we physicists, what we call proof, and this will come into play when we talk about string theory in a minute, but what we call proof is really not up to mathematical standards. So what do you mean by, intuition comes first and rigor comes second? Why is that acceptable to a mathematician but not to a physicist?
Okay, so there's a lot going on in that question. First, let me just say Archimedes did prove a formula for the area of a parabolic segment. Just to remind people what that is. So that's if you cut across a parabola with a line, making a shape that is, some bounded region that has a parabola on the bottom and a straight line on the top. Roughly speaking, he's finding out the area under a parabola. Yeah. And he can do it. And he does it two different ways, and it's totally rigorous, and it would meet any standard that we have today. It's just that he doesn't use the fundamental theorem of calculus, because that won't be invented for another 2,000 years or so.
Right.
But he knows how to do it by adding up smaller and smaller triangles and taking a limit. He doesn't call it a limit, but he's using an ancient technique that they called the method of exhaustion that squeezes the area. Anyway, these are details, but anyway, he had intuitive ideas about how to solve the problem, just like every mathematician, and I think every physicist has a bodily feeling, has a hunch, has experimental clues. You have something that is short of rigor at first. You have an idea of what should be true. Like we sometimes say, it's morally true. Like this really should be true, but we don't see why it's true. And so but first comes this feeling and often a desire. So it's not just a feeling or a hunch, but it's I want it to be true because this thing is beautiful or this thing is so cool. I just want it to be true. And so then you set out to find a reason why it has to be true. And if you're lucky, you're right. Then your conjecture was correct and you found a proof, a series of cold-blooded logical steps building on axioms, or in the case of physics, building on known physical laws that lead you by deductive reasoning to the thing you thought was true. But yeah, hunches come first. Intuition comes first. I mean, it's true. You ask, John Lennon or somebody, how does he write Imagine? Or, what's a great show? Song Exploder. Do you know this show? Song Exploder is an interesting show you can watch. I think it was a podcast, actually. And musicians talk about how they wrote this famous song. Like the guys in REM talk about how did they write Losing My Religion, or how does anyone do anything creative? And they tell you, well, I was just playing around on the ukulele and I thought this was kind of a really cool thing. It wasn't the song at that point. It was just a glimmering. Right. So it's all like this with everything. How does a poet write a poem? They don't just sit down and write it. They have a feeling. So it's the same in math. You have some intuitive desire and a vision of what you want to create, and then you have to have the technique to create it. And in math, that technique is rigorous proof, or calculation, or whatever.
Sure. So just finishing up with that and then circling back to Richard Feynman and his conversation with Herman Wouk, who we began the podcast with. Richard Feynman said, I don't care how beautiful your theory is, what beautiful math it uses. If it doesn't agree with experiment, it's wrong. In the case of physics, obviously that's one standard. But I've had many guests, Kamran Vafa comes to mind, who have said things that essentially string theory is too beautiful to be wrong, and that in the everlasting, enduring time capsule question, which I will soon turn to you, he answered he would put the equations of string theory on a monolith to launch into outer space for all time. I want to ask you, what about this? Where do you fall as an applied mathematician, kind of hybrid between the physical universe that I explore with colleagues in the purely theoretical mathematical world of physics or math? What about things like Michio Kaku says, there's 10 to the 500 different string theories, and you have to tell me what the initial conditions are, but you can't tell me because the initial conditions vary from universe to universe. So are we just lost? It's been said that the math of string theory is from the 21st century or the 22nd century, and it fell into the 20th and 21st century. Now, what do you make of this? Do you think that string theory is too beautiful to be wrong, sort of morally true, as you just said?
Well, so this is way outside anything I know about, so you shouldn't pay any attention to what I have to say. I don't know, never studied even quantum field theory, so I'm certainly in no position to talk about string theory. But as just a general matter, that's a disturbing point of view, the idea that something is too beautiful to be wrong. There have been a lot of beautiful theories that have turned out to be wrong. So I'm surprised at my physics friends who say that. It certainly turned out to be, in math, a lot of great math has come about as a result of string theory. For instance, there's this great thing about knot theory, the Jones polynomial, which Ed Witten figured out a deep explanation for this cool invariant of closed curves that have knots tied in them. The Jones polynomial is just kind of an oddity that worked, but we didn't really understand why it had its miraculous properties. And then Witten was able to kind of embed it in a deeper theory that explained where the Jones polynomial was really coming from. And I think, and I may be wrong about this, but I think it was some insights from string theory that gave it to him. So this didn't really help, or maybe it's topological quantum field theory that gave it to him. I don't know. But the point being, beautiful physics may really help us in math. As to whether it helps us understand the universe, sometimes yes, it did with general relativity. Sometimes no. There have been beautiful, so far, the jury's out on supersymmetry, right? Supersymmetry seems to be beautiful, but we're not seeing it yet in our experiments, as far as I know.
Right.
So it could be that it's wrong. It just may be that our universe isn't built that way. I don't know. But it's still worth studying. That's the thing. Just the love of beauty has usually been a good guide. It may not be our particular universe, but we'll learn things by doing it, and it will at the least give us some really cool math. And it may give us some really cool physics. I don't know. I don't begrudge the physicists working on string theory for that reason. But it is embarrassing for them.
Suck up all the oxygen. It's
it does suck up a lot of oxygen. It does.
Yeah.
It does.
Yeah.
It does.
Almost
Yeah,
the
that's interesting.
Of other theories. And there are some that say, it hasn't led to, so anything, as Nathan Seiberg said, if we discover something beyond string theory, we string theorists are very arrogant. We'll call it string theory. And in fact, I had that on my podcast recently, these discoveries of the muon's anomalous magnetic moment, so-called G-2, and phenomena like this Large Hadron Collider beauty quark discovery that indicates a fifth force. So as soon as the result comes out, string theorists will say, yes, that's what string theory would tell you. But no one ever looks into the string theory and says, oh, well, here's where this is going to come. Apparently, because there are too many potential initial conditions that each one can produce a different value for G-2 or something like that. So it's a conundrum. As I say, I actually asked Michio Kaku this before. I said, well, you're very gung-ho and bullish on string theory, but what if you're the director of the NSF and you get two proposals, and one is for string theory and one is for not, minus, whatever theory or Strogatz theory, and how do you
don't fund that?
Fund both, he said. And I said, well, that's a nice, kind of like saying I'll have the chicken, if you can't decide between the fish and the tofu. But anyway, Stephen, I want to thank you, and I want to ask you also if you are willing to go into the impossible and answer the 3 trademark patented questions that I ask all my beloved guests, and you would be no exception. I want to ask if you are willing to play the Into the Impossible thrilling 3 final questions.
Let's do it. Okay, sure. Why not?
Okay. So the first one involves what we in Judaism call a zava'ah, or an ethical will. And it's actually not too dissimilar from something that Alfred Nobel did. He had no children, no wife, no heirs of a direct lineage. And so he left all of his money to those that benefited mankind. In other words, it wasn't just a material will to benefit their bank accounts. It was to benefit all of mankind. Sort of unique. And in Judaism, there are many examples of this. And one of which is, of course, Jacob blessing his children, and Moses, the book of Deuteronomy. Anyway, I don't get too religious here, although I'd love to do that with you separately. As you know, my rabbi said, after my interview with you on The Joy of X, on your wonderful podcast, to which everyone should subscribe, rate, review, and do whatever you can to support it. I love that podcast. It's one of my regular rotations. But he said, you and Stephen should become study partners in Torah. We should be.
That would be fun.
havrusas, which means friends. But it also,
Nice.
and I've learned so much from you, and it's kind of temeritous for me to suggest that I could teach you anything. But anyway, Steve, this is a long way of saying, when you reach the biblical age of 120, many years hence, what do you want to leave the world, your biological, but also your ideological heirs, in terms of wisdom or teachings that you've learned?
Well, on my Twitter page, it says, all cards up, face up, all the time. And that was something that my friend Charlie Marcus said to me once. He's a physicist, actually, working on quantum computing. And he actually will be another guest as a turn. You know how it is. You invite your friends onto the show, right? So, yeah, Charlie Marcus is coming up in a few weeks on the Joy of X. But Charlie said that about me, that, man, with you, it's all cards up, all cards on the table, face up all the time, like no filter, nothing secret. And I'm reminded, too, of my high school yearbook quote. You know how it is in your high school. You have to pick out something to put in the yearbook, and you don't know, because you're at such a formative stage in your life. You don't really exactly know who you are and what would you want people all those years later. They're going to look at your photograph. Oh, I remember that guy. So, then you want some little saying or something, a song lyric that's going to capture who you were at the time. So I think, was it in high school? Or was it in college? I can't remember. But the one that seemed right to me at the time was a quote from Mark Twain, who said, if you tell the truth, you don't have to remember anything. Kind of like that one. I still like that one. If you tell the truth, you don't have to remember anything. You don't have to be cunning. You don't have to be full of guile. Just tell the truth. And it's a little easier. It's a little more efficient. It's not always the compassionate thing to do. So I don't want to go too far, Telling the truth in unpleasant circumstances can be mean. So you have to temper it. But I also like this line from Mark Kotz. So that's of Feynman-Kotz formula, KAC, a Polish mathematician. Mark Kotz said, with regard to teaching, tell the truth and nothing but the truth, but not the whole truth. Right? A little play on what we make people say in court, Tell the truth and nothing but the truth, but not the whole truth. The beginning student, you shouldn't be lying to the student for the sake of simplicity. You should just tell the truth and no lies, but you don't have to tell the whole truth. That's going to be too complicated at first. It takes a while to absorb the whole truth. So don't lie, but don't tell the whole truth first.
And this is something in your interview with Shane something or other on the Knowledge Project, the Farnham Street podcast from a couple of years ago. Yeah, Shane Parrish, you said something beautiful. It was like, give students, and this echoes John Mather, winner of the 2006 Nobel Prize, his advice from David Wilkinson, who is my advisor's advisor. He said, get good students and give them impossible problems, but don't tell them they're impossible. And you said almost the exact same thing. So I thought it was beautiful, this role that you so wonderfully exemplify as an educator.
Wow. David Wilkinson, man, that's so cool that you're connected to him. He was a freshman physics teacher back when I was taking physics at Princeton.
That's right. Yes. And I think we talked about
legendary teacher. Yeah.
Yeah. He was, he is sorely and deeply missed. I have an interview. I'm doing an interview. One of my interviews in a couple of weeks ago, I did was with my PhD advisor, Peter Timby, who was his student as well. So he was my conduit to David Wilkinson. So we talked a lot about David and about people like Robert Dickey and other people. So yeah, that'll be fun when that podcast comes up. Okay, so next, Steve, I ask all my beloved guests, what material object or knowledge would you put on your monolith? And the monolith is meant to be evocative of these structures in Arthur C. Clarke's 2001 A Space Odyssey, these menacing kind of time capsules that are placed around the universe and sprinkled around, meant to be found when humanity has the capability to understand it by some unseen ancient alien civilization. Now, we agreed by rule of NASA that we're not going to talk about the alien autopsies. But if you were going to leave a time capsule, what would you put in it or on it, or what would it be about? And I could give you Feynman's answer, your fellow or former Cornell
Yeah.
professor. He used to say it was the cataclysm question. He said it was the atomic hypothesis. Everything is made of atoms. I wonder, what would you say? What would encapsulate the most information about the physical or mathematical world that kind of you'd use to brag, you'd use to flex on future civilizations?
Yeah, well, it's certainly not my discovery or anything like that, just as the atomic hypothesis is not exactly Feynman's either. Yeah. But Seed magazine, which I don't think exists anymore. Seed magazine was a magazine that had the tagline, "Science is culture." And science was often portrayed in that magazine as a kind of a cool thing. They would have artists talking to mathematicians or scientists, and it was very interdisciplinary, nice magazine. Too bad it's not printing anymore. But once they did have an article about Feynman's quote about the atomic the cataclysm question, or whatever you want to call it. What would you leave if a cataclysm was going to come? What one sentence would convey the most information? So I actually was asked that question at that time and wrote something into Seed, which is what I would still answer today, which at the time I didn't have a name for it, but now I would call it the infinity principle. I think that would be my answer, that to make sense of anything that changes smoothly, any shape, any motion, any process, any phenomenon, no matter how wild it is, break it up into infinitely many, infinitesimally small, straight pieces that behave like constants, and then solve the problem for those little pieces, and then put the answers back together again to make sense of the original whole. So that principle is the essence of calculus. And
yes,
I think it's one of the greatest ideas humanity's ever come up with. So that would be it for me.
In contradistinction to Feynman's answer, because the atomic hypothesis suggests that there's an ultimate, what does atom stand for again? Indivisible?
Yes, uncuttable.
Right. So
right. Indivisible.
Principle of Strogatz. We'll see in 2,500 years which one lasts.
Well, his is probably right. I mean, the atomic one is probably true. This one is not true. This is a creative fantasy. But it's it's so close to true, and it's so fruitful. Whereas his does not generalize that well in math.
Yeah.
You can't do much with discrete math compared to continuous math. I know that some people will say I'm nuts for saying that. But I think time has shown that the calculus beats the pants off anything in discrete math.
Yeah. And I can't wait to see what comes after calculus when we're in a post-calculus universe. So, Steve, we've gone forward in time to your leaving this mortal coil at age 120. We've gone 1 billion years into the future. Now we're going to go backwards in time. Again, hearkening, as I do, to Sir Arthur C. Clarke, who's the namesake behind the Arthur C. Clarke Center for Human Imagination here at UC San Diego, where I co-direct it along with my friends and family members. And that is one of his laws. He had many laws, Steve, one of which is any sufficiently advanced technology is indistinguishable from magic. And I actually have his voice saying those very famous words open every podcast, as you'll hear, hopefully, when you listen to the podcast in a few weeks when it comes out. His second law applies to our fellow members in the faculty club, UCSD and Cornell, and that is for any expert, there's an equal and opposite expert. And his last law, or his third law, states the only way of discovering the limits of the possible is to venture a little way past them into the impossible. That's the origin of this podcast name. And I want to ask you, as a 20-year-old, advice to your 20-year-old self, your 30-year-old self, what aspect of life was most mysterious and perplexing? What piece of advice could you give a young Steve to give him the courage to do what you've done, to go into the impossible?
Well, I think of myself as the weakest math major at the time in college. That was an important part of my self-image. I would see the other kids raising their hand before mine would go up. They would see the answers. They could carry out arguments more precisely, go deeper. And it was discouraging to be around such smart people and to feel like maybe I don't have the right stuff to do what my dream was, to be a professor and to teach and to learn and, maybe discover something here and there. And it was a cause for concern. But Princeton had a requirement. Every senior had to write a senior thesis. And I wrote about something. I was interested in geometry, but I also was interested in the real world. And I thought about geometry of DNA molecules. I had been learning about DNA and biochemistry courses and biology. And anyway, so I didn't know if I would really be able to discover anything or not about that. But it turned out, just sort of through good luck and good connection with a biochemistry professor, I kept going to him with ideas. He would say, "That's a terrible idea," and he'd send me away. And my math professor my advisor would also say, "Well, it's good that you're learning some biochemistry, but I hope you'll come up with some good math." Anyway, I just kind of stuck with it. And eventually, this biochemist, Abe Worcel was his name, Abraham Worcel, said, if you really want a good problem, this is the problem you should work on. And he described a certain question to me. He said, everyone's breaking their head about this. If you could solve this would be good. And I said, well, I could do that this afternoon. And he said, are you crazy? He was from Argentina, and he would get very hot, and jumping around. And he'd say, Dad, you're crazy. You don't understand the first thing. Let me explain it to you again. So he starts explaining it again. But I did understand it. And it turned out that all the suffering I had done up till that point in the year, all my dead ends, put me in a position to understand his question. And it was actually an easy question if you knew the right things, which I had learned in the course of being stuck. And so I did solve it that afternoon, and I showed him, and he was hopping around the lab saying, this is going to be big. And anyway, so it was my first paper. And the reason I'm telling the whole story is my advice to my old self would be, don't worry about not being the smartest. Love goes a long way. Love of your subject, love of your art, and the passion. Like, you have to get lucky, which I did. But stick with it and love it, and don't worry. There were always going to be people smarter and better than you, but there's still a place for you.
That's great to hear, Steve. And it's just so, I'm listening and I'm thinking, I heard you once describe, maybe in that same interview with Shane, about, how you proved this conjecture in high school to a mathematician who had gone to MIT or professor, and then no one had ever solved it, he claimed. And then you solved this thing about triangles, something about triangles. And I'm thinking, this was the weakest math. It solved 1,000-year-old geometry problem. And what hope is there for me? But I think I'm going to spin it around for our friends at Princeton and say it's a testament to the brilliance of mathematicians around the world that even Steve didn't consider himself the greatest of all. Anyway, you've gone on to influence the world in such a positive way, Steve. You've influenced me. Now you're influencing my father-in-law. That's a gift that you just cannot beat. When you give a guy something that he can give to his father-in-law and make him teach him something that his son-in-law is not a stupid moron. Steve, I want to thank you so much. You're such a mensch, as I call you. You're the mathematics mensch. But I just appreciate you so much, and I'm so glad that you don't keep all your discoveries to yourself like that hateful Gauss. Share them. Not only your mathematical discoveries, of which Steve is by some counts one of the most cited physicists in history, and as a mentor and studies the art and craft of science presentation. You can find his lectures all over the internet. But I please want everybody to subscribe to The Joy of X, even if it means not listening to an episode here and there of this podcast, Into the Impossible. Please do that. Leave a rating for Steve on iTunes. And Steve, I just want to thank you so much. And I do hope we'll meet in person someday.
Me too, Brian.
Here or in Ithaca.
Thank you. This is a really beautiful interview and fun conversation. It's going to be great when we get to do this in person. Thanks a lot for having me.
Any sufficiently advanced technology is indistinguishable from magic.
If you enjoyed this video, click here.